Before we jump to MATLAB and see how we can compute and plot the dynamics of the position and velocity of a mass spring damper problem, let us first of all analyze and solve the problem. So here is our problem. A mass spring damper system with a mass of 1 kg, a damping coefficient of 5 Newton per meter per second, and a spring constant of 2 Newton per meter is initially displaced by 0.8 meters and released to move freely with zero initial velocity without any external force. So we are asked to use MATLAB to compute and plot the dynamics of the system's position and velocity over a period of 10 seconds. And you can see it has an external force of F of t, and it has a spring and a damper which are opposing the applied force. Y of t is used to represent the displacement. K is the spring constant and C is the damping coefficient. So let us see the solution. So we are going to use the Newton's second law of motion. Summation of F is equal to my double dot, and our summation of F consists of the applied force, the damping force, and the spring force. So assuming the applied force is in the positive direction, then the other two forces will be negative, and my double dot is in the other side. So our damping force is just C times the velocity. C is the damping constant as earlier on defined, and K is the spring constant. So we have F of t is equal to 0. Why is it equal to 0? Because in our problem it is stated that after the system is displaced by 0.8 meters, it is released to move freely with zero initial velocity without any external force. So it's the movement after it has been released is without any external force, therefore F of t is 0. So our equation will reduce to my double dot plus cy dot plus ky is equal to 0. So here are our model parameters, and our model reduced to y double dot plus 5y dot plus 2y is equal to 0. So now we will have some definitions. Let y1 to be equal to y, which is equal to the position, and our velocity to be y2, which is equal to y dot. Therefore y2 will be equal to y1 dot. So substituting this definition to this equation, we'll have y2 dot to be equal to minus 5y2 minus 2y1, and y1 dot will be equal to y2. So defining a capital Y vector to contain our position and velocity variables. The first derivative of this vector will be y1 dot and y2 dot, which are earlier on computed. So this first order derivative model is the model required by the ODE45 function. Apart from that, it also needs the initial values of the position and velocity, which from the question are 0.8 meters and 0. So let us jump to MATLAB and see how we can implement this solution over there. So the left screen contains what we need to know for using the ODE45 function. In MATLAB, the indexing of a vector starts from 1. Therefore, y1 is equal to y of 1 and y2 is equal to y of 2. So we need to come up with a function that gives out y dot, which is defined by y2 and minus 5y2 minus 2y1. And we do that over here in the right hand side. I define a function known as MSD, which is an abbreviation for mass spring damper, and it has as input the time, which is the independent variable, and my y vector, which contains the position and velocity, and the output of this function is the y, which is the derivative of the vector. So here are my system parameters. C is 5 and k is equal to 2, and my d1 is just obtained from here. So the first row is y2, which is defined based on the indexing, and moving to the second row, I have minus 5y2 minus 2y1, which is just minus 5y2 and minus 2y1. So this is the first derivative model, and now we move to its implementation in the other script. So this is the ODE45 function. So here is the handle of the function that defines the model. So this is the first argument. The second argument is the period of time over which you want to obtain your simulation, and the time span is 0 to 10 as given in the problem. Third argument is the initial values for our position and velocity, which is defined over here, 0.8 meters and 0 meters per second. So the rest of the code is how I come up with my plotting as well as visualization of my position and velocity variables over time. So as you can see, this is just the code and you can first to go over it. So now running the script. So as you can see, I have my position in red and my velocity in blue. So the initial value, it's set as 0.8, and eventually, because no force is applied to it, it goes to 0. And you can see the velocity is like a negative velocity because the position is going down, and it also goes to 0 over time. So you can use this script to see how changing the parameters of your model affect the system. After reducing the damping coefficient, the system will be more oscillatory. So if you make it 1, we expect our system to be more oscillatory. So you can see there is some oscillation before it goes to 0. So we know that if the spring constant is 0, after releasing the spring, it will just remain stagnant. So we can also visualize that. So as you can see, the initial position remains as 0.8 meters and the velocity remains as 0 because the spring constant is 0. So you can play with the parameters to see how changing them affect the system dynamics. Another thing that I want you to see is the variables that I use for my plotting. We have the t, which is just the time, and we started from 0, t is equal to 0 up to period of 10 seconds. So my y has two columns. The first column is for the position. As you can see, the initial value is 0.8 and the velocity is 0, as you can see. So over time, up to 10 seconds, you can see the position goes to 0.011, which is about 1.1 centimeters, and the velocity is still negative. If you want to learn how to solve simultaneous equations in MATLAB, watch the video on the screen. Thank you.